So good evening, everybody. So we are having some network issues today, and this is because there was a great thunderstorm here this afternoon and a huge downpour. So I think you understand the situation. So we have some couple of speakers today, student speakers, and then we have our guest speaker by guest speaker, Professor Dimitri Batani. And finally, we have another session for our student speakers. So they will be live soon. So before we start today's session, I would just like to name a few of the presenters this evening. One is Shomo Sarkar, another is Moinak Chatterjee, and there are some, just a moment, there are some another speakers. Well, we start with Moinak Chatterjee from Barashat Government College. The title of his talk is Iron Acoustic Shock Fronts and Solitary Structures, the effect of exchange correlation of electrons. So, Shomo, could you just start sharing your slides?
Sir, I am going to start, isn't it?
Yes, sure. Moinak, I think.
Moinak, yes, sir.
Yes, thank you.
Okay, sir. Sir, I am sharing my slides. Are they visible?
Yes, they are visible. You can just carry on.
Okay, sir. It is not going away. Just a second, sir. Okay. Good afternoon, everyone. Myself, Moinak Chatterjee. Today, I am present over here to present
There
our
is
work.
one window just open on your first slide. Just okay, okay. It's it,
Is it okay, sir?
Yes, yes, yes.
Okay. So, once again, good afternoon, everyone. Myself, Moinak Chatterjee. Today, I am present over here to present to you all the work that we have done in the workshop, in the plasma workshop. So, first of all, let me introduce you all to my group members. These, as you can see on the slides, are my group members. The first one is myself, Moinak Chatterjee. Beside me is Moitri Haldar, and adjacent to her is Meghna Dasgupta, and is followed by Shayani Das. Okay. Now, before I start the presentation, I would like to acknowledge the help and support of our friend, philosopher, and guide, that is our mentor, Dr. Swarniv Chandra, sir, without whose guidance it would have been just impossible for us to complete this work. Along with this, we would also like to thank our parents, who had always been a source of support and moral encouragement to us and had been with us all through the project. Okay. So now let's move on with our presentation. The title of our talk, as said and as you saw in the first slide itself, is Analytical Studies of Ion Acoustic Shock Fronts and Solitary Profiles in a Weak Relativistic Semiclassical Plasma with Exchange Correlation of Electrons. Okay. So let's start. Now, I think everyone amongst us have listened to the speakers who presented previously in the previous days of the webinar, and I think we all have got from it a basic idea that what plasma basically is. But still, for those who have joined the live stream today only, I would like to repeat the things briefly once again. So now, what is plasma? Just like the three other known states of matter, that is the solid, liquid, and gas, plasma is considered to be the fourth fundamental state of matter, which contains a gas of ions, electrons, and some neutral particles. We know that at very low temperatures, almost all substances are in the solid state. Now, as the temperature is slowly increased, the particles get more energized and their intermolecular distance of separation increases. Now, when after attaining a certain temperature, the distance becomes so large that the state changes and the substance becomes a liquid. On further heating, the liquid gets converted into gas. Now, if the gas is further heated to very high temperatures, say almost 20,000 degree Kelvin or higher, the electrons present in the outermost shell of the atoms get enough energy to jump out of its orbit and become free. This creates, in fact, a soup of ions and electrons. And this soup is basically called the plasma. That is the fourth state of matter. This state was first described by an American chemist, Irving Langmuir, in the 1920s, most probably in 1928. So, this is how the fourth state is described theoretically. Now, we have described it theoretically, although, but still we require certain evidences to verify whether this description of ours is valid or not. So, in other words, we need to see this fourth state. That is, we should see plasma in order to verify its existence, isn't it? We see that if plasma comes in contact with air, it will cool down, and the ions and the electrons present in it will recombine to form neutral atoms. Thus, our experiences to plasma in this terrestrial world of ours is very limited. But still, there are some examples. They are first, as you can see on the slide, is the flash of lightning bolts. As the streaks of thunder produce very high temperature, the path followed by them, that is, the path followed by the bolts, get ionized and they become plasma. Although they don't become so permanently, but for a very short time, but still they become one. Second one is the glow of the auroras. That is the aurora borealis and the aurora australis. Okay, I will cover this part, that is the formation of auroras and how they are formed, in a later part of the presentation, which I'll be coming up in a few minutes only. So the next one we can see in polar winds, which are the permanent flow of plasmas arising from the poles of the earth. Which generally form due to the interaction between solar winds and the earth's magnetic fields. Along with these, there are certain type of fluorescent lights. That is, you can say the tube lights or the fluorescent lights, which contain plasma state within them. Okay. But outside Earth, plasma is found abundantly. It can be said easily that more than 90% of the visible universe is made up of plasma. Although, in fact, the visible universe is only the 4% of the total universe, but as the 96% of the remaining universe is made up of the dark stuffs, that is the dark matter and the dark energy. But out of those 4%, 90%, in fact, more than 90% of the matter is in plasma state. Now, outside Earth, plasmas can be observed in the stars, where they are formed on being heated by nuclear fusions, in the interstellar and the intergalactic spaces, which are the spaces between the stars and the galaxies, in the atmosphere of certain hot planets, and in an active galactic nuclei, that is at the center of the galaxies. Also, they can be found in the accretion disk of black holes. Okay. Now let us move on to the properties of this fourth state of matter, that is the properties of the plasmas. There are three major properties of plasma. The first one is quasi-neutrality. The plasma, this state of matter is considered to be quasi-neutral. That is, it's neutral enough such that the ion density, that is the density of ions present inside the plasma, is roughly equal to the density of the electrons present inside it, which roughly is equal to the plasma density as a whole. But even though with this neutrality, the electromagnetic forces don't vanish from within the plasma. That is, the plasma is neutral overall, but the electromagnetic forces still do exist within it. Now, the collective behavior. Collective behavior implies that the motion of one plasma particle is not only depending on the local conditions relative to that plasma particle, but also on the remotest conditions relative to it. I mean, if something happens at one of the remotest corner of the plasma, that plasma particle which we are considering will also get affected. The third one is device shielding. Device shielding is basically a phenomena within the plasma where any electric field, either created or introduced externally, is neutralized within a very short range. The distance after which the effect of the electric field is nullified is called the device length and is given by this expression, which you can see on the screen, given by lambda d. So this is the basic expression for the device length. Now, along with these three properties, there are three more conditions which distinguish a plasma from any ordinary ionized gas. These are, first, that the lambda d should, that is the Debye length, should be very, very less than 1. That is, the electric field introduced or formed inside a plasma should be nullified, or you can say should be neutralized very quickly within a very short range. Next one is the plasma density, that is Nd, should be very, very high. That is, Nd should be very, very, very greater than 1. The third condition is that the product of omega into tau should be greater than 1, where omega is the frequency of plasma oscillation and tau is the mean time period between the collision of a charged particle with a neutral atom. The product of omega into t should be greater than 1 so that the motion of the plasma particles is not controlled by collision only and is controlled by the electromagnetic forces. So, thus we have covered some basic topics of plasma physics. Now let us move on to our project, that is the work that we have done in the workshop. Let us understand what acoustic waves are. Based on the vibrating particles, that is the particles that are vibrating within the plasma, whose motions we are basically considering, the plasma can be categorized into four types of acoustic waves. The acoustic waves, you can see the GIF, the way the motion of the particles are creating a wavy pattern. So there are four types of acoustic waves. These are the ion acoustic waves, in which the motion of the ions are mainly considered, the electron acoustic waves, in which the motion of the electrons are being considered, the dust acoustic waves, in which the motion of the dust particles and the neutral particles in plasma are being considered, and electrostatic waves, in which both the motion of the electrons and the ions are being considered. Okay. Now, in the workshop, we worked with two such acoustic waves, that is the ion acoustic wave and the electrostatic wave. First of all, what we did was that we analyzed these waves and then found out their respective dispersion relations and the 2D plot of the dispersion relation and the damping relation, which we will be covering up in a minute. Thus, moving on with the ion acoustic waves. I mean, first of all, we found out the dispersion relation of two types of waves, ion acoustic waves and electrostatic waves. Then we carried on forward with the ion acoustic waves, and then we found out their KdV Burgess equation, which whose full form is Korteweg-de Vries Burgess equation, in order to study the solitary structures and shock profiles which are going to be generated in that type of wave, and then plotted its respective 2D and 3D plots to further extend our study. So, yes, the slide is visible. Okay. So the governing equations that you can see are the basic equations which we use to study the ion acoustic and the electrostatic waves. These are the 5 equations. The first two are the continuity equations of the electron and the ions. The second two are the momentum equations for similarly the ions and the electrons, and the third one is the Poisson's equation. Now, one may ask that why we are considering only the continuity equation, momentum equation, and Poisson's equation only. I mean, there are so many type of governing equations possible in physics. So why are we considering only these 3 type of equations? Well, you see that actually the plasma is a fluid, and all fluids follow the hydrodynamic equations, and that's why the equation of continuity has been considered. The first 2 equations, as you can see on the slides. Along with these, as the plasma particles are always in motion, the conservation of momentum equations are to be considered as well. Those are those are depicted by the next 2 equations, the third and the fourth one respectively. Now, the plasma contains electrically neutral, sorry, the plasma contains electrically charged particles. So for electrically charged particles, we see that the Maxwell's equations are a must. There's 4 set of Maxwell's equations. But along with that factor, as we are considering unmagnetized plasma in our case, so the 3 Maxwell terms containing the B, that is the magnetic field, get vanished. And we are left with the Poisson's equation. So which makes the 5th equation of our study. Okay. Now you can see the UXE term in the 4th equation, which denotes the exchange correlation term. It is considered in order to include the exchange of energy between the moving particles. Due to this exchange, the damping occurs sometimes, which can be seen in the dispersion relation plots, which we will be seeing in a bit. Now, these 5 equations contain terms having different dimensions and units. These create the calculations cumbersome and difficult at the same time. Thus, we normalize these equations using proper normalization schemes so that our equation doesn't contain any dimensional term. So these are the normalizing equations conditions. These 6, as you can see, I'm moving my cursors over it. And then we are using the classical pressure expression, this one. And using these normalizing schemes and pressure equation on the governing equations we saw on the last slide, we get the normalized equations for both the electrostatic waves and for the ion acoustic waves. So these are the governing equation for the electrostatic waves, these 5. And yes, slide has changed. These 3 are the normalized equation for the ion acoustic waves. Now, you may ask that why we are considering the only 3 equations in case of ion acoustic waves. As we know that ion acoustic waves basically lay emphasis on the motion of the ions and not on the electrons. So the electrons equations have been neglected in this case. And so we are getting 3 such equations. Okay, now you're using the perturbation relations as you can see in the slide. And now with the help of these perturbation relations, and when we operate these on the normalized equation, we get the relation between the plasma frequency and wave vector, that is omega and k. The first boxed equation is the one for the electrostatic waves, and the second boxed equation is for the ion acoustic waves. Now, the real part of these 2 equations give us the dispersion relation, and the imaginary part when plotted gives us the damping relation. Now, the slide has changed. Yes. Now, these is what exactly the dispersion relation and the damping relation plot looks like when plotted. So these are for the electrostatic waves, and the first one, the plot on which I'm moving my cursor, is the dispersion relation plot for changing values of u0. U0 is basically the stream velocity of the particles, and this is the damping relation plot. We see from the dispersion relation curve of the electrostatic wave, that is the first one, that almost on the very beginning itself, the dr plot attains a constant linear growth, having a constant slope u0. That is the stream velocity of the particles, as I said before. From the damping plot also, we find that initially there exists a non-zero damping effect. See, basically, when we look at the damping plot at the very first glance itself, it appears to be the plot of y equals to 0, isn't it? But on zooming on the very beginning of the plot, we see, as it has been shown in a zoomed picture, there exists a non-linearity which attains a constant value very soon, and the constant value tends to 0. You can see it is of the power x to the power -7. So you can understand how close it is to 0. That's why in the bigger graph, that is the second one on which I'm moving my cursor, it seems that it is just parallel to 0. So there exists a changing non-zero damping effect which exists for a very short time, and after which the damping effects become constant and tends to 0. Now, similarly, these are the dispersion relation and damping plots for the ion acoustic waves. These three, the first three are the dispersion relation plots for changing, for different changing parameters. In the first plot, the value of mu, that is the ratio between the mass of electron and mass of ion, has been changed, and we have obtained this relation, this plot. The for the second value, the mu has been changed, sorry, the eta, that is the coefficient of viscosity, has been changed, and we have obtained this plot. And for the third plot, we have changed the values of u0, that is the stream velocity, and have obtained this. Along with this, we see that the damping plot is somewhat like this. Now we find from the dr graphs that they basically consist of two parts, one the nonlinear part and another one the linear part. We observe that the nonlinear part exists till the value of k reaches the value fourth root of 4 mu by eta I square, and after that the graph attains linear growth. One second. Sir, are my slides visible? Because it just vanished from my screen.
Yes, it is visible. Yes, it is visible.
Okay, sir. One second. I think there's some problem in connection. Okay, yes. It has appeared once again. Okay. So we observe from these three graphs that the nonlinear part exists till k reaches the value fourth root over of 4 mu by eta I square. And after that, all of a sudden, the graph attains constant linear growth. And from the damping plots also, that is the fourth one, we find that initially there exists a non-zero damping effect, which reaches its maxima at the same value of k, that is this same value, fourth root over of 4 mu by eta I square, and then vanishes sharply and becomes 0. So the observations from the damping plot confirms our analysis of the dispersion relation plot, as now we can correlate the two type of graphs together. As we can see that as the damping effects increase from the damping plot, the velocity, that is, okay, from the dispersion relation plot, we are basically the group velocity, that is del omega by del k, by from the slope of the dispersion relation plots. So we see that when the damping effects are increasing, the group velocity is getting diminished for a certain period of time, and as soon as the damping effects tend to 0, the group velocity, as we can understand it easily, that they will attain a constant velocity, and that's what is being shown in the dispersion relation plots as well. So now let us move on to another section. We will see what solitons and shock waves are in plasma. For that, we first need to understand what a solitary wave is.
Moinak, we are running
Yes, sir.
short of time already. Could we just
Okay, sir.
move a bit fast?
Okay,
Because
sir. Okay, sir.
we
Okay,
have
sir.
just.
Okay, sir. So as we can see, a solitary wave is a localized wave, as you can see in the picture, whose pulse width remains constant and as well as its amplitude. And a soliton is similar to a solitary wave, just that it maintains two such conditions, that its shape when it's moving with constant velocity should remain constant, and when one soliton collides with another soliton, the shape of two solitons should remain unchanged with possibly a phase shift. A shock is a different type of disturbance in a medium which travels faster than the speed of sound in that medium and is generated by an abrupt change in the pressure, temperature, or the density of the medium. Now, there's a basic difference between solitary waves and shock waves. That is that solitary waves amplitude doesn't decrease with time, but in shock it does happen so. Now, these are the stretching expressions which now for which we have used for plotting for deriving the KdV Burgess equation. These three are the stretching equations. We are using stretching basically to zoom into the pictures to get a detailed analysis, and using the stretching expressions and the perturbation relations, and by substitution and elimination we are getting this KdVB equation, this one, the boxed equation. Now we are using a transformation, and we are getting the solution as this: phi is equals to 12 dn 1 minus tan hyperbolic square zeta minus 36 r by 15n tan hyperbolic zeta. Now we see that the solution has got two parts. One is the tan hyperbolic zeta term, and one is the 1 minus tan hyperbolic square zeta. The first part signifies the solitary profiles, and the second part denotes the shock profiles. So we will see in the next slide itself that more the shock profiles. Wait for a second. One thing I forgot to say is that the more the coefficient of tan hyperbolic zeta is, the more the solitary profiles will tend towards the shock profiles. And as we can see that this coefficient depends on r, that is depends on eta. So as eta increases, we can see that the plots will move on from solitary waves to shock waves, as we can see from the first plot itself. Initially, for lower values of eta, there exists a symmetry as is being shown by the red and blue lines, but on increasing eta, there is introduced an asymmetry, and it tends towards the shock waves. Now, these are the 2D and their corresponding 3D plots. From these, we observe that the greater the difference between the phase velocity and stream velocity, higher is the peak. Also, the more viscous a plasma, the faster the potential peak drops, and the lesser the mass of the ion, more is the effect of the potential peaks on it. Okay, so now we have come to the conclusion. From the detailed study of the plots that we analyzed, we got the basic properties of the ionocaustic waves in plasma and noted that their behavioral dependencies on different parameters like phase velocity, stream velocity, viscosity of the plasma, and the ratio between mass of electrons and mass of ions. Thus, we can conclude that due to the introduction of nonlinearities in the ion oscillation, a huge number of positive ions YOLO.
Hello. Is there any network issue, Moina?
Yes, sir.
Yes, it's okay. Apple. Just start with your PowerPoint again.
Yes, sir. Yes, sir. 1 second. Is it visible, sir?
No. You start presenting. Share screen.
My screen is already being shared. So I think I got removed.
You just log out and can we just join again in Zoom?
Okay, sir. Okay.
I think that would be fine.
Sir, I will do the same from my mobile phone only.
Okay.
It
Fine.
will save time.
And just remove your video. I think that's taking
Yes,
up
sir.
much of a bandwidth.
sir, are the slides visible?
Yes, yes, they are visible. Just go to the point where you stopped. Go.
Yes, sir, yes, sir. Thus, we conclude that due to the introduction of nonlinearities in the ion oscillations, a huge number of positive ions gather within a very small region, thus resulting in the sudden upsurge of positive potential peak. And due to the formation of such a positive potential peak in plasma, the ions present there are strongly repelled by it and are accelerated to supersonic velocities in a short span of time, thus giving rise to shock waves in plasma. Also, the more the height of the potential peak, the more will it be interaction with the particles, and as a result, higher peak potentials repel the ion with more force and attract more negative charges, which result in the increase of negative potential on the right side of the peak. So this is how we can explain the formation of solar flares and auroras as well. That is, a similar phenomena occurs in the sun, due to which the particles, the plasma particles present over there are accelerated to supersonic velocities, and they travel up all the distance between sun and earth, and on entering the earth's atmosphere they interact with the atmospheric particles over there and excite their excite the electrons present in the outermost shell of the atoms, and when those electrons return to their ground state, they emit light which are generally seen by us in the form of auroras. Okay, so these are some of the references that we have used for doing our work, and this is all I have got to present to you all. So thanks patiently for listening to me, and sorry for the minor glitch that happened and due to the network connection. So thank you, sir. Thank you, everyone.
Thank you, Moinak. Uh, so far, we have visitors, and if they have any questions, they can put forward. Um, I think that was a good introduction because all these things we have been doing as for an introductory part of plasma physics, the
Yes, sir.
solitary profile, the dispersion curve, these things are quite fundamental, and Moinak has clearly elaborated those for students who are, or the listeners who are very new to the today. And we thank Moinak once again.
Thank
And
you,
you are
sir.
getting a lot of applause because it was
Oh,
crystal clear and you have presented very well. Thank you.
thanks,
So I
sir.
would just suggest
Thank you,
uh,
everyone, for praising the
the next speaker, I think the next speaker has sent one presentation online, and it is a pre-recorded one, and he is also here present with us. So uh, we will just run that record, or we have Professor Batani with us again now. And sir, would you like to join now? Sir, will it be fine for you? Hello, sir, will it be
Sorry,
fine
did
for
you
you?
say if I like to join now?
Yes, sir.
Yeah?
Yes, sir. Will you deliver your talk now? Is it okay?
Yes, it's okay.
Sure, sure, sure. Then we'll just have a flip of our schedule, and Professor Batani will present his talk. So those who are new today, for them, I would just like to give a few or say a few words about Professor Batani. Professor Batani is one of the most illustrious scientists in the field of laser technology and currently a professor in the University of Bordeaux, France. He has a research career spanning over more than 3 decades and has got more than 10,000 citations. And he has carried out his research work prior to France in Italy, Milan. So he has contributed profoundly to the understanding of high power laser matter interactions, essential for both for inertial confinement for fusion and for creating secondary sources for X-rays and high energy protons. Professor Batani is a member of the Institut Universitaire de France since October 2015. He joined Bordeaux in 2011 after a long career in Milan. He obtained his PhD from University of Pisa in 1990, and he has been a visiting professor here in India in Jadavpur University. So we have met quite a few times back, and he has always been with us. His love for India, especially Kolkata, is very well known. Thank you, sir, for being with us. We heartily welcome you in this evening, sir. And today his uh, lecture would be on the advances in inertial confinement fusion. Thank you, sir.
Thank you.
Could you
Sorry.
just turn on your video? Yes, sir.
Yes. So do you see and do you hear me?
Yes, it is okay. I can see
Okay.
what.
So I will share my screen
Yes, sir.
to put the presentation. And so let me see how we, okay.
Yes, sir. Thank you.
Okay, so thank you very much again for inviting me for this second talk. So yesterday we spoke about fusion in the laboratory, mainly magnetic confinement fusion, and in the universe. And today I will speak about inertial confinement fusion, which is more directly related to the work which I do as a researcher. So this is what we said yesterday. There are three approaches to create the condition for fusion. In stars, you have gravitational confinement, which is that the plasma, the hydrogen plasma, is confined to very high density and for very long time in the star. And these allow to have fusion directly from protons. On Earth, we are not able to have a long confinement time and big densities at the same time. So we either have low density and long times, which is the principle of magnetic confinement, or we have big densities and short time, which is the principle of inertial confinement fusion. And also on Earth, we are not able to make fusion starting from hydrogen, because this involves a very long reaction chain, which is difficult. And we can only try to make fusion starting with isotopes of hydrogen, like deuterium and tritium. And actually, as I mentioned yesterday, you also have a fusion in a non-controlled way in the hydrogen bomb. And in a way, as we will see today, inertial fusion is like a very small hydrogen bomb, but of course, let's say that there is no real explosion because the mass of the fuel is very small, and because the trigger is, of course, not a conventional nuclear bomb, but it is lasers. So the principle of inertial confinement fusion is that you take a sphere of frozen DT. You start with frozen DT because you want a high density of deuterium tritium, and you want to further increase this density by compression. You shine the laser beam all around these spheres. This produces ablation of the material, which produce a very hot and very rapidly expanding plasmas, which expands outwards. And by conservation of momentum, that is the third Newton's law, you get a compression of the remaining mass. And this compression increases the density and increases the temperature. And finally, if everything goes well, you may reach the conditions which are needed to trigger the nuclear fusion reaction. Well, actually, there are two big pathways to inertial confinement fusion: the so-called direct drive and the so-called indirect drive. In direct drive, you shine the laser, as I shown before, directly on the target. In indirect drive, the target, the fuel, the DT sphere, is contained within a case, of IZ material, something like gold or uranium. And you shine the lasers on the walls of this case, which is called hole round. On the walls of this hole round, you create a plasma, a hot plasma, which emits X-rays. And the implosion, the ablation and the implosion, are produced not by the laser, but by these X-rays. So what is the advantage of having indirect drive? Well, of course, you have a clear disadvantage because here you use all the laser energy to compress the target. In indirect drive, you have an intermediate step of conversion of laser light to X-rays. And this can kill 50% of your efficiency. But the advantage of indirect drive is that because of the confinement within this cavity, the X-ray radiation soon become very similar to a black body radiation. And the black body radiation has many beautiful properties, including the fact that it is uniform and isotropic. So it means that this target is irradiated in a very uniform and isotropic way. So ablation will be the same everywhere, evaporation will be the same everywhere, and this target can implode very uniformly, remaining a sphere which reduces with time. In direct drive, any non-uniformities of the laser beam reflect directly on the uniformity of compression. And as we will see later, this can have dramatic consequences and may imply that you are not able to reach the condition for nuclear fusion. Well, either you use direct drive or you use indirect drive. Today, we know that you need a megajoule class laser system. That is laser pulses, which of course cannot be done with only one laser beam, but you need multiple irradiation beams, which in total deliver megajoule energy. Well, this is the real example of all round. With the typically this is, let's say, 1 centimeter by 2 centimeters. And this is how the laser beam enter through the holes, through the 2 entrance holes, and irradiate the walls of the round. Well, the fact that researchers have privileged indirect drive because of the uniformity problem reflects directly on the design of the laser. So these are typical design of lasers like the National Ignition Facilities at the Lawrence Livermore National Laboratory, or the laser megajoule in the French Atomic Energy Commission near Bordeaux. And you see that this laser beam do not come uniformly around the interaction chamber. So they don't come uniformly around the target, but they come in 2 poles, up and down. And this is indeed the 2 poles which correspond to the 2 central holes of the round. Actually, National Ignition Facility is a laser which became operational in 2009. It is the biggest laser in the world, and nowadays it can deliver 2 megajoule of ultraviolet light on target. Laser megajoule is almost the twin laser of NIF. There are small differences, but let's say they were designed together in the 90s. And it is still not completed. I mean, not all the beams or not all the laser beams have been installed, but the facility is already operational. The third biggest laser facility in the world is the Shenzhen 3 laser in China, which is also used for studies on inertial confinement fusion. Well, just to relax a bit, these are some pictures corresponding to the installation of the National Ignition Facility. And you see the dimension of the National Ignition Facility. They have 3 football grounds. This is American football, I guess. This is the interaction chamber, which is 10 meters in diameter. And you see all the ports for the laser beam, the square ones, and the ports for the diagnostics. And you see the interaction chamber was put in place, and then the building was built around the interaction chamber. Again, this is the interaction chamber as it is nowadays, with all the beams entering in the chamber. And this, for the science fiction lover, is an image taken from the movie Star Trek. And actually, a part of this movie Star Trek was turned around the interaction chamber of NIF. This is the scheme of laser megajoule. Well, actually, I said that it is almost the twin laser of NIF. Actually, if you look at NIF, you have the interaction chamber and all the laser beam, what is called the laser bay, are on one side of the interaction chamber. In laser megajoule, you have laser bay on one side and another laser bay on the other side. There are some other small differences between megajoule and NIF, but let's say that the main design is the same. And you see that this building is 300 meters long and it is 40 meters high. Just to make comparison, if you compare with the Taj Mahal, this is the main building in Taj Mahal is 100 meters long and it is a bit higher, it is 68 meters. So basically you can put 3 Taj Mahal, one after the others here. And this is a view of the interaction hall, where you have the interaction chamber, which is again 10 meters in diameter, and you have, and you have 176 beams which enter into this chamber and are finally focused on that small hall room, which makes 1 centimeter by 2 centimeters. So here you can see the size of humans for comparison. Now, let's go more in details about the physics. A typical inertial confinement fusion target is made by at least 3 layers. There is one external layer, which is called the ablator. This is either plastic, glass, beryllium, or synthetic diamond. This is the material which you sacrifice. I mean, this is the one which by ablation is converted to expanding plasma, okay? You do not have any interest of shining directly on the deuterium ice, deuterium tritium ice, because this is your fuel and you want to keep it until the end. And also the Z number, the atomic number of these ablators is bigger, of course, than the atomic number of hydrogen, which means that the absorption of the laser light is improved because it increases with Z. Then the second layer is this DT ice, and the density of this DT ice is 0.25 grams per cubic centimeter. And this is a shell. And then in the middle, you have some gas, DT gas. The typical radius is about 1 to 2 millimeters, and the typical deuterium tritium mass is about 1 milligram. Well, of course, why you could say why it must be so small? Well, actually, it is so small because if you have a bigger mass, you have so much energy which is released from the fusion reaction, which really looks like an explosion. Indeed, the 10-meter chamber of NIF or of LMJ must be 10 meters because you have to absorb the shock produced by the release of energy from the fusion reaction. If you make a smaller chamber, the power per unit surface will be bigger. It will increase with the inverse of the square radius. And indeed, the chamber will not be able to survive many shocks. So we are bound to use a very small mass because we want to have controlled nuclear fusion. So we have to control the explosion. Of course, the bad side of this is that if we have a small mass, the number of fusion reactions will be limited. And so for future production of energy, we must have a very big repetition frequency. That is, we must shot one target after the other in order to get a big production of energy. And this is, of course, a very big technological problem, because you must consider that lasers like NIF are single-shot lasers. So today technology is not able to produce megajoule laser which shoot in repetition rate. In NIF you can get, they got a record of 3 shots per day. Maybe there could be 4, but for the production of energy, you would need to shoot at least at 1 Hertz repetition frequency. So you can imagine that the technological gap in laser technology between where we are now and what we need for nuclear fusion is still enormous. So we speak about ignition or break-even when the energy released by the fusion reaction equals the energy delivered by the laser for compression and heating of the target. And in order to get the condition for ignition, we must be able to compress the fuel at about 1,000 grams per cubic centimeter. So the initial density was 0.5 gram per cubic centimeter. So it means that you have to compress the DTIs 4,000 times. And then we have to heat the temperature of at least the central part of the target to temperatures of 510 kV, which, as we saw yesterday, are the minimum temperatures by which you can trigger fusion of deuterium and tritium nuclei. Well, this approach, which I just described, let's say we compress the fuel and we heat the center, is called ignition by central hotspot. Why do we need the hotspot? Well, the answer is simple. If you consider a typical target, radius 2 millimeters, and you will see, you consider the volume and the thickness, you will see that the mass is about 1 milligram. 1 milligram of DT contains about 2 10 to the 20 ions. Well, if you want to heat all these ions to give them a typical kinetic energy corresponding to a temperature of 10 kV, then you end up with the energy of 1 megajoule. Well, 1 megajoule in the fuel. As we will see later, we have a 1 megajoule laser today, but we are not able to put 1 megajoule of energy in the fuel. Most of the energy goes into the creation, into the ablation process and in the creation of the plasma, what we call the plasma corona around the target. So if we have 1 megajoule laser, we will see in a few moments that at most we are able to put in the fuel 100 kilojoule. So if this shows that volume ignition, the approach in which we try to heat all the ions to 10 kV, is not achievable with present-day technology. So the approach that we follow is quite different. We try to compress the target. It is possible to show by simple calculation that compression does not require a huge energy. Heating is more expensive in terms of energy. So we compress all the target and we just heat the central part. We just heat the gas, the DT gas, which was contained in the center of this shell. And then in this shell, we will get 10 kV. We will start the fusion reaction. We will produce alpha particles and neutrons. Now, alpha particles and neutrons play a completely different role in our approach. The neutrons, they are small, they are not charged, so they have a very long penetration depth. So basically, they escape from this compressed target. And actually, they will be the way by which we recuperate the energy released by the fusion. Instead, alpha particles, they are more massive, they are charged, so the penetration, the mean free path is very, very small. So the alpha particles, which are released in the center, they will just penetrate in the first few microns of the compressed fuels around the hotspot. And then, by stopping there, they will deposit their energy, and they will increase the temperature of this layer. And by doing so, in this layer, we will reach also the condition for fusion. And then the process will repeat again and again. Now, alpha particles and neutrons will be produced in this layer, and they will deposit in the following layer. So we speak about a thermonuclear burn wave, which gradually progresses and uses all the fuel. So this hotspot is actually, you could ask, why do we need to use a shell? Why we cannot use a full sphere of DT? Well, actually, the point is that if you use a full sphere of DT, it is more difficult to compress and more difficult to heat. Instead, compression and heating becomes easier because what you do, you accelerate this shell. You accelerate the shell inwards. And then, as the shell becomes smaller and smaller, the gas inside becomes also compressed and warmed. So its pressure increases. At a given time, the pressure of the gas will be so strong to equal the external pressure and will be so strong to slow down and stop the implosion of the shell. So basically, we get the hotspot by converting the kinetic energy of the imploding shell into thermal energy of the hotspot. So I said that the shell slows down, and when the pressure of the fuel and the pressure of the hotspot are the same, you get what is called stagnation. And this shows that indeed you are getting an isobaric fuel assembly. The center has the low density because you have started from a gas and you are compressing it, but still it is lower, and a very high temperature. The shell has very big density, but a lower temperature. And the pressure is the same everywhere. Typically, at stagnation, we want to have the density of the fuel, as we said, 1000 grams per cubic centimeter, and we want to have the temperature of the hotspot about 10 kV. And then the equality of the pressure implies that in the hotspot you must have about 100 grams per cubic centimeter, and in the shell you must have about 1 kV. And also, if you assume as a reasonable number that the hotspot has a size of about 40 micron, then you will see, and the mass is about 2.7 10 to the minus 5 gram, which is small because you're starting with the gas, you will see that the energy, the thermal energy contained into the hotspot is about 30 kilojoules. Okay, this scheme, isobaric fuel assembly, is of course a simple model. This is the reality, I mean, it's the reality from simulation of a National Ignition Facility target imploded with 1 megajoule of laser energy. And you see that, of course, you don't have this square profile, but still you can identify hotspot where the density is low and the temperature is big, and you can identify a dense shell with a very high density and a smaller temperature. Now, the condition in this hotspot and in the dense shell are very different because due to the fact that the density here is relatively low, I mean, it's still very dense, it is 100 grams per cubic centimeter, but the temperature is very high. So the hotspot, the plasma in the hotspot is a perfect ideal plasma, is a perfect gas. Instead, this one is degenerate matter. So it's not completely degenerate, it's not completely described by the Fermi theory, but it is matter with a high degree of degeneracy. So if this is a perfect gas, it is easy to calculate the pressure because the pressure is just the density times the temperature. And you see that in the hotspot, the pressure will be 600 gigabar, 600 million bars. Sorry, billion bars. Well, actually, this also shows why it is important to use a spherical geometry. You know, the laser, by shining the laser and through the ablation mechanism, we can produce a pressure of about 50 megabar. And we saw that the pressure stagnation is about 500 gigabar. So it means that we need to increase the pressure applied by the laser of about 10,000 times. And actually, this increase comes to convergence. You are going from 1 millimeter. If you are going to from 1 millimeter to 100 micron, you have a reduction of a factor of 10, which means that the volume is increased by a factor of 1,000. And pressure is an energy density. So in this case, pressure will be increased by 1,000. So in this case, we need a bit more to get 10 times more. And this is only possible by using the spherical geometry. There are designs for the future in which it might be possible to use cylindrical geometry, which could be in a way easier. But the problem with cylindrical geometry is that you still have convergence, but it's not so big as in the spherical geometry. So this is about the story of the target during, this is the story of the target during implosion. And basically you can identify 5 phases. The first one is ablation and acceleration. So here you have the laser which shines, produce ablation, and put in motion the ablator and then the DTIs. Then you have the free flight, and again the laser here is still shining and is reducing the mass of the ablator. Eventually, at the end of compression, you want the ablator to be 0. Then you have a deceleration phase because the pressure in the hotspot begin to increase and slow down the shell, the imploding shell. And then you have stagnation, where the two pressures equal to each other. So if you consider a mass of fuel of 1 milligram, in order to get 30 kilojoule in the hotspot, you see that you need an implosion velocity, which is about 350 kilometers per second. This is simply by equating the kinetic energy of the imploding shell to 2 times the hotspot energy. I put the 2 here because actually this kinetic energy roughly goes half in heating up the hotspot and half in compressing the fuel. So you can imagine that 350 kilometers per second, which means 350 micron per nanosecond, is a very high velocity. So how you get this velocity? Well, actually, this is produced by the ablation. The implosion of the target, the set in motion of the target due to ablation is really the same, can be described as the set in motion of a rocket. So in a rocket, you have the rocket which moves because it expels hot gases. And by Newton's third law again, the quantity, the momentum in this direction is balanced by the momentum in the other direction. And you have this equation which tells you that indeed the acceleration of this target is due to the expulsion of the gas, and you have with time a reduction of the mass. Well, this is well known. It is contained in many physics books at the bachelor's level. And the velocity of the rocket is finally described by this equation, which tells that the velocity is equal to the expansion velocity of the gas, to the expulsion velocity of the gas, times the logarithm of the remaining mass. Well, of course, you see that by rockets, you can reach any velocity, okay? In principle, you can go up to the velocity of light, but okay, you have to include the relativistic correlation. But in order to get very big velocity, you need this remaining mass, this fraction of remaining mass, to be very, very small. So it means that you need a very big rocket, and you almost use all the mass to, almost all the mass will be expelled. Indeed, we know that rockets are very good to put satellites in orbit, for instance, but they are very inefficient. You need a big rocket to put in orbit a small satellite. Indeed, if you calculate the efficiency of the rocket, this is just the kinetic energy of the remaining mass divided by the kinetic energy of the mass which is being expelled. You see that a classical rocket can have a maximum efficiency of 60% for a remaining mass of 20%. Well, this is a classical rocket. For inertial confinement fusion, for laser-produced plasma, the situation is much worse because in addition to the kinetic energy of the gas, you must also consider that this plasma is very hot. So it brings away kinetic energy, but it also brings away a lot of kinetic energy. And this reduces the efficiency by a factor of 4. So instead of 65, you get something like 17% maximum energy conversion efficiency. And indeed, remaining mass of 0.2 is not what we want, because if we have a remaining mass which is 20% of the initial mass, it means that we have ablated most of the target, which means that the remaining shell is very, very thin. And the shell which is very thin is very fragile, and it can break during implosion. And we will see that this is a very serious problem in ICF. So a more suitable choice is to have a remaining mass about 50% of the initial mass. And in this case, the maximum energy conversion is about 12%. So typically, if we have 1 megajoule laser, the typical maximum absorbed laser energy will be 1.1 megajoule, because you have some light which is refracted, some light which is reflected by parametric instabilities, and so on. And then you have 1.1 megajoule, and you have a maximum conversion efficiency of 12%, which means that at most you can couple to the target 130 kilojoule. And roughly, as I said before, 50% go of this 130 kilojoule go to hit the spot, and 50% go to compress the fuel. Okay, this is again the, let's say, some kind of summary of what I said. You know, the hot spot is hit by the conversion of the kinetic energy of the imploding shell into thermal energy, and the conversion efficiency from laser to the shell kinetic energy is very low. Okay, here is 5%, which is maybe more realistic in experiment as compared to the maximum theoretical of 10%. And again, okay, this is really the same view graph, but it just shows that if in addition you are using the indirect drive approach, you have the intermediate step of conversion of laser light into X-rays, and this again kills the total efficiency of your system. Again, some orders of magnitude. Again, if you have a radius of 2 millimeters, and before stagnation you want to reach an implosion velocity of 400 micron per nanosecond, it means that the average velocity during implosion will be maybe 200 micron per nanosecond. I mean, you see here, 400 kilometers per second will be the velocity in this free flight region. But if you start from the beginning to the stagnation, it will be something like the average velocity will be of the order of half of this maximum velocity. So if you have a 2 millimeters radius and an average velocity of 200 micron per nanosecond, it means that the implosion will last around 10 nanoseconds, which means that you need a laser pulse which roughly is 10 nanoseconds in duration. And then the other conclusion is also that if you have 1.5 megajoule and you consider the surface of this sphere, you get an irradiation intensity of 3×10⁻⁴ watt per square centimeter. So everybody who has been working with lasers knows that such an intensity is very easy to reach. I mean, you get a small laser, you focus it on a small focal spot, and you can easily get 3×10⁻⁴ watt per square centimeter. Nowadays, as you know, we can get a short pulse laser, which can get intensities on target of 10⁻⁻² or 10⁻⁻21 watt per square centimeter. So the intensity which is used in inertial fusion is not at all exceptional, but the energy is exceptional. And the energy is very big because you have a very big surface to be irradiated, and you need a long pulse. Well, there is also another point which is very important in inertial confinement fusion, which is in a way the opposite of what we have said until now. So until now, we have said that we want to reach very high implosion velocity. So which means that we want to have very fast implosion. But in this very fast implosion, we must also be in a way, very slow and gentle. We must realize what we call a quasi-adiabatic compression. What does it mean? It means that if we get our DTIs and we compress it too violently, too quickly, we produce heating of the fuel. And of course, you know that if you have matter which is warm, it is more difficult to be compressed as compared to matter which is cold. So in a way, we have to do this compression, which is very fast, in a very gentle way, without heating matter more than needed. So the type of compression which heats matter the less is isentropic adiabatic compression. So we want to, with the laser, we want to try to make a quasi-isentropic adiabatic compression. So how can we do it? Well, we do it by laser pulse shaping. Instead of arriving with the laser, which is 3 × 10⁻⁴ watt per square centimeter from time 0, we start with an intensity which is much smaller, and gradually we increase the intensity. So basically what we want to do, we want to increase the intensity so that the ablation pressure increases with time to match the compression of the target. Well, we are not completely able to do this today. So in experiment, what we do, we introduce an adiabat parameter alpha, which is the ratio of the pressure which we would achieve in a perfect isentropic compression to the pressure which we really achieve in the experiment. So let's say if we do a perfect adiabatic compression, our alpha would be 1. If we make a compression which is a bit more violent, we can have alpha which is, let's say, 1.5, which means that instead of putting the fuel at one given pressure, the pressure will be 1.5 times this pressure. Now, we have these two opposite requests, to get very high velocity and to get gentle compression. Well, in order to get very high velocity, again, we need to use a small mass. So 1 milligram was a limitation due to the fact that we want to control the release of energy, but it's also a limitation because we need a shell to be thin so that the kinetic energy will be big. Of course, I mean, the kinetic energy can be big because you increase the mass or because you increase the velocity. But the dependence on velocity is square, so it's much more effective to reduce the mass and increase the velocity if you want to get big kinetic energy. Well, the problem is that a thin shell, as I said before, can break during implosion. And if it breaks, the implosion stops, and you will not be able to reach the condition for triggering the nuclear fusion reaction. Well, actually, this is related to a well-known instability, which is the Rayleigh-Taylor instability. Okay, I guess that you know the process of the Rayleigh-Taylor hydrodynamic instability quite well. But just to summarize, if you have air and water, of course, the water will not drop because the air pressure is bigger than the pressure produced by the gravitational force. But this is true if you have a separation surface. If you don't have a separation surface, the water will fall. It doesn't fall because of gravity, because gravity is smaller than the force related to pressure. It falls down because of the development of Rayleigh-Taylor instability. So you can imagine small modulation on this surface, and the modulation will be amplified in time. And the classical growth rate of the instability is related by the Atwood number, the wavelength of the perturbation, and the acceleration. And of course, you see that if you have water, air on water, the situation will be stable. And if you have water on air, the situation will be unstable. Well, this is the classical growth rate of the Rayleigh-Taylor instabilities. In laser plasmas, luckily, this is partially stabilized. This is known as a Takabe formula, by the name of the Japanese physicist. And actually, there are two mechanisms by which the Rayleigh-Taylor instability is stabilized. The first one is due to the scale length of the produced plasma. L is the scale length of the plasma, which means that instead of getting a step function change in the density, you have the density which gradually changes in space. And the second one, so it basically means that it reduces, let's say, reduces the space where the Rayleigh-Taylor instability can grow. And the second one is due to the ablation velocity, because you are creating you are starting to grow the Rayleigh-Taylor instability in one place, but this plasma is taken away by the ablation. These are just examples of a hydrodynamic simulation showing the Rayleigh-Taylor instability in the linear phase and then in the nonlinear phase. And then in inertial confinement fusion, Rayleigh-Taylor instability can be very active in two phases. It can be active in the acceleration phases, and it can be active in the deceleration phases. Here, it can be active on the ablation surface, because here you are trying to push a dense material, the shell, using a very low material, the plasma corona. So it's just like the case of air, which is trying to keep the water, which is more dense. And in the deceleration phase, again, the gas inside the hotspot, low density, is trying to decelerate the dense shell. Well, let's come to result of experiment. In 2009, the Lawrence Livermore National Laboratory started the National Ignition Campaign. So they were really very optimistic about the fact that they could show that they could achieve ignition. And actually they said that they were going to achieve a gain of 20. So it means that the NIF was delivering 1.5 megajoule of laser energy, and they were expecting 20 times more. So 30 megajoule released by nuclear fusion reaction. For comparison, if you have a gain of 1, it means that you are producing 5 × 10⁻17 neutrons. And so they wanted to produce 20 times more neutrons. In reality, in experiment, they only got about 10⁻15. So they were very optimistic, but they failed to achieve ignition. And well, this is due to many reasons coming at the same time. And indeed, these experiments were designed by complicated numerical simulation. And in this simulation, you need a lot of ingredients. And of course, you need equation of state data on the materials, because you want to see how they compress when you apply pressure. You want to have data on opacities, because you need to generate X-ray radiation and absorb it at the wall or the around, and you need to absorb the X-ray radiation on the target. And it turns out that both the equation of state data and the opacity data were indeed incomplete. And then there was an underestimation of the impact of parametric instabilities in the gas inside the round. The round was not empty. There was a low density gas, because the goal of this low density gas was to slow down the expansion of the plasma from the walls of the round, because otherwise this expanding plasma could fill the round and then the laser beam could not penetrate. And then there were other problems, like how they keep the pellet, the DT target inside the round. They were using a very, very thin foil, and they thought that this was no effect. And indeed, it turns out that this was producing very strong non-uniformity in the compression. And then probably the main point, which was the cause of the failure of the national campaign, was the underestimation of Rayleigh-Taylor instabilities. Actually, the Rayleigh-Taylor was much stronger than predicted, and the shell broke before the end of the implosion. So, after, well, if we can say one comment, this clearly shows that achieving ignition is not just a technological challenge, but it is still a scientific challenge, and as such is somewhat unpredictable. You can more or less predict where technology will go in 10 years from now. You can not predict scientific evolution, because you can always find obstacles which you didn't expect. And this is true for inertial confinement fusion, and this is true for magnetic confinement fusion as well. Well, what happened after the end of the national ignition campaign? Well, basically they continued the experiment, and then they got much better result. You see, this is the neutron yield in kilojoule during the national ignition campaign, and from the shots which were made later. So basically, they were practically multiplying the neutron yield by a factor of 10. But this is a very important result. But the second important result, which is also maybe more important, is that in this new implosion, the contribution from the contribution to the thermal energy of the fuel due to the self-heating produced by the alpha particles was comparable to the heating produced by the slowing down of the imploding shell. So maybe I tell this again. Of course, when you have this shell, you will have heating, as we have said, due to the conversion of the kinetic energy of the shell. But then, if you start to have nuclear fusion reaction, and you always have some nuclear fusion reaction, then you have alpha particles, and there is heating, additional heating produced by alpha particles. Now, you see that during the national ignition campaign, the heating produced by alpha particle was negligible compared to the heating of the kinetic shell, of the kinetic energy of the shell, and then it became comparable. And this is very important, because if you remind the principle of the hotspot ignition is that you must be able to produce a number of alpha particles which is big enough to produce this thermonuclear Born wave. So alpha heating is the key to nuclear fusion ignition. And you see, for instance, these are some more detailed analysis of the shots. And you see that in these shots, for instance, the energy in the hotspot due to the conversion of the kinetic energy of the shell was about 4 kilojoules. And the energy, additional energy produced by the deposition of energy of the alpha particle was about 2 to 3 kilojoules. So we are entering alpha heating regime, which is bringing us much closer to ignition. So how did they get this result? Actually, they get this result by changing the laser shape. As we said before, we need to have a quasi-isentropic compression. So we need to start with the intensity which is low and increase it very slowly. So what they did, they use, and this is called low-foot laser pulse. What they did, they used a high-foot laser pulse. So they started with the intensity, which at the beginning was bigger. So in a way, this is a surprise because they were using a wrong laser shape. So you are shining the target with the laser intensity, which is bigger. So you produce more heating. You're producing a alpha adiabat parameter, which is bigger than 1. Typically, the alpha parameters in low-foot implosion can be something like 1.5, and in high-foot implosion, it can be 2 or something like that. Well, so why you get a better result by using a worse laser pulse? Well, actually, it is related to the Rayleigh-Taylor instability. You see, if you look at the growth rate of the Rayleigh-Taylor instability, which we saw before, this is the formula. And if you have a high-foot laser pulse, the intensity is bigger. Intensity bigger implies that the velocity of ablation is bigger and implies that you create a longer plasma, a plasma with a longer scale length. And these two facts contribute to reduce the growth rate of the Rayleigh-Taylor instability. So these are simulations of a low-foot implosion. You see adiabatic parameter 1.45, and you see that the effect of Rayleigh-Taylor instability is very strong, and at some point the shell is going to break. And this is the simulation with the high-foot laser pulse. The parameter is almost 3, but the impact of the Rayleigh-Taylor instability was much smaller. Now, these are most recent results from the National Ignition Facility, and they changed other things. They changed the type of ablator they were using, for instance, beryllium or synthetic diamond and so on. And they got to this point where they have 2 10 to the 16 neutron per shot and 57 kilojoule of fusion yield. In this shot, the alpha heating is the energy contribution produced by alpha heating is 2 times the kinetic energy, the contribution due to the kinetic energy of the shell. So here we are just a factor of 20. Let me just go back a second. Yeah, gain equal 1 is 5 10 to the 17, and now we are at 2 10 to the 16. So we are just a factor of 20 far from ignition. And this factor of 20, when you look at all the progress which is made, it really does not seem impossible. So I think that in the future few years, we may expect the National Ignition Facility to demonstrate ignition with gain of 1. Well, this will be an enormous scientific achievement. but it is still not good for future production of energy. And actually, you see that indirect drive does not seem compatible with future fusion reactors because the targets are very complicated, which means that it will be very difficult to produce and to align them at a very high repetition rate. And they are massive because you have these cylinders of gold or uranium, which is a centimeter size. And each shot, this is completely destroyed and injected into the chamber. And if you think that you will make shot at 1 Hertz, after 1 day, you will have deposited on the chamber a very big mass. And above all, indirect drive is intrinsically low gain because due to the intermediate step of conversion of laser light into X-rays. And finally, indirect drive also poses political problems because it is considered very similar to a very small hydrogen bomb. So it is considered as a proliferating technology. I think that this problem has been a bit exaggerated, but still it shows that for future reactors, we need to move to direct drive approach. Well, the problem of direct drive is that it is even more sensitive to Rayleigh-Taylor instability because every non-uniformity of the radiation of the laser due to the laser will act as seed of the Rayleigh-Taylor instability. So how is possible to mitigate the impact of Rayleigh-Taylor instability in direct drive? Well, the idea is that it will be possible to separate the compression phase and the ignition phase. In the central hotspot ignition approach, which we have considered until now, the task is very difficult because in the implosion, you have to do 2 things. You have to compress the fuel, but also you must be able to heat the hotspot to very high temperatures, which means that you need to have a very big velocity of the imploding shell. If you can decouple these 2 phases, everything will become easier on paper, of course. And this is what we try to do with 2 approaches, which are called fast ignition and shock ignition. Okay, what is fast ignition? Well, in fast ignition, you compress the target. You don't care. I mean, we are able to compress. I mean, the result of many experiments has shown that we can compress matter to very high density. But maybe we are not able to compress matter in a very uniform way. So we are not able, because of this non-uniformity of compression, we are not able to hit the spot and we are not able to trigger the condition for nuclear fusion. But if we don't care too much about the way we compress matter, we can compress it. And then once matter is compressed, we use a very high intensity laser to interact with the plasma and to produce a beam of relativistic electrons. And these relativistic electrons it is supposed that they will travel to the dense fuel, deposit their energy, and produce the increase of temperature, which can trigger the nuclear fusion reaction. So in a way, the comparison between the normal hotspot ignition and fast ignition is like the comparison between a normal car engine and the diesel engine. In the normal, let's say, most used car engine, you compress your gasoline and then you have an ignition spark. In the diesel engine, you compress the fuel and you don't have this ignition spark. It's just the compression which produces the heating and the burning of the fuel. Well, this concept of fast ignition is very interesting, but unfortunately, it is beyond the state of present-day laser technology. because for fast ignition, we need the laser which can be able to deliver at least 100 kilojoule in less than 10 picosecond over 10 micron. And if you look at the present day petawatt laser system, the biggest laser system like ARC at the Lawrence Livermore Laboratory, or LFX in Japan, or Petal in CA in Bordeaux, they can deliver maybe 1 to few joules. 1 to few kilojoule. And so 100 kilojoule is really beyond what we can do today. So why do we need to get such big energy? Well, we need to have a hotspot which has the order of 10 micron, and we need to heat it at 10 kV. And if you make the calculation, again, the energy in this hotspot will be about 10 kilojoule. And then the irradiation time must be very short, because you want to deposit this energy before hydrodynamic motion. And there are a lot of problems related to fast ignition, because we have to study the propagation of very high intensity laser beam in the plasma corona. You have to study the generation of fast electron. You have to propagate the electrons between the critical density where they are generated and the dense core. And they have to deposit the energy. There are some positive answers, in the sense that we are able today to produce electrons with the required energy, typically 1 MeV. I mean, if they are too energetic, they will cross the target without penetrating the energy, without depositing the energy. And we are able to convert a large fraction of the laser energy to electrons. But still, there are many, many physical issues, and the propagation of the fast electron in the dense material is also very difficult to be studied, because not only you have the collisional effects, the stopping power, which are described by the Bethe-Bloch formula or similar, but because you are moving a large number of electrons in a very short time, you have very high currents, which means that you have a generation of very big electric and magnetic fields. And actually, these self-generated electric and magnetic fields are much more important in determining the dynamics of the electron beam as compared to collisional effects. And this is an additional difficulties, because collisional effects are basically one particle effect, single particle effects. But this generation of electric and magnetic fields is a collective effect. Their strength depends by how many electrons you are moving, which means that you can do experiment today with a laser which has maybe 100 joule and 1 picosecond, but it's not easy to scale the physics to the regime where you will have 1 picosecond and 100 kilojoule. So, and then one of the main problems of fast ignition is also that at the moment we don't have a clear idea of how to control the divergence of these electron beam which we are creating. Of course, if you create a parallel beam, it will deposit the energy in a very small spot, which will be heated to very high temperature. But if the beam is diverging, then the energy will be dispersed. And the result is that maybe instead of needing 100 kilojoule laser, you will need a much bigger laser. So in conclusion, fast ignition is an interesting idea, but for many aspects, it is beyond the present day of technology. And because we don't have the laser which are needed, we are also limited in studying the physics which is related to fast ignition. The other approach which I was studying before, shock ignition, instead has the big advantage of being compatible with present-day laser technology. So how it works? Well, this is a laser pulse shaping in the normal classical hotspot ignition. You need to reach implosion velocity of 400 kilometers per second, which means that you need a thin target. The fact that the target is thin means that the thickness is much smaller as compared to the radius, which means that what we call the aspect ratio of the target is high. In shock ignition, you make the implosion of a target which is thicker, and you make the implosion at lower velocity. So, because of this, the laser pulse will compress matter, but you will not create the condition in the hotspot. So at the end of the compression phase, now you have another spike, which is typically a duration of a few hundred picoseconds and intensity of 10 to the 16 watt per square centimeter. I remind that here you were at about few times 10 to the 14. And these final laser spikes create a very strong shock which travels inward, converge to the center, and hit the fuel to create the condition for nuclear fusion. So basically, just to say, in shock ignition, the main compression beam does not need to create the spot. Then, because you don't need to create the spot, you can reduce the implosion velocity. And one way to reduce the implosion velocity is to use a thicker target. And the thicker target is in itself less sensitive to hydrodynamic instability. It is more resistant against the impact of Rayleigh-Taylor instability. Well, there has been some preliminary experiments. These have been done at the Omega Laser Facility in the United States. Now, the Omega Laser Facility is probably today the 4th or 5th laser in the world concerning the dimension, concerning the delivered laser energy. But it's not a megajoule laser facility. I mean, they have something like 60 kilojoule of laser energy which are available, which means that in Omega, they cannot hope to make ignition. So in a way, the laser Omega is a very good platform where you can study the physics before moving to megajoule laser system. The advantage of the Omega laser facility is that it is a facility which has been designed for direct drive. So the laser beam are coming in a uniform way around the target. So what did they do? They made the implosion using two different pulse shapes. A pulse shape which reminds the hotspot approach, and a pulse shape which looks like shock ignition. And they were measuring the neutron yield in these two kinds of implosion. Actually, in this graph, what is reported here is not directly the neutron yield, but it is another quantity which is the yield over clean, the yoke. Actually, this yield over clean is the ratio of the neutrons that you get in the experiment compared to the neutrons that you are expecting from the result of 1D hydrodynamical simulation. So in 1D hydrodynamical simulation, you have, of course, spherical geometry, but you are not able to describe the perturbation of the surface. So 1D hydrodynamic simulation do not take into account, cannot take into account the impact of Rayleigh-Taylor instability. So here, what do we see? We see that when they use the usual, okay, here the colors unfortunately are exchanged. I mean, the blue here correspond to the red here. But you see, with the spike, the yield over clean was much better than without the spike. So the yield over clean was still very low. I mean, it was 5% here and 10% here. So they were getting only 10% of the neutrons which were expected according to the 1D simulation. But still, this improvement in the yield over clean shows that the quality of the implosion is much better. It shows that the impact of Rayleigh-Taylor instability is much smaller. So it shows that you are closer to 1D. You are closer to a perfect, you are more close to a perfect implosion where there is no hydrodynamic instability. Of course, this is, as I said, a preliminary experiment because it has been done on a facility which is 60 kilojoule instead of what you need. But still, it is very encouraging. Well, so shock ignition still looks promising, but still we have many physical unknowns. The first one is that at intensity of 10 to the 16 watt per square centimeter, we know that the laser plasma interaction will be dominated by parametric instabilities. There will be a huge impact of stimulated Raman scattering, stimulated Brillouin scattering, and to plasmon decay. So it is very important to study how they develop, how much light they reflect. Raman and Brillouin scattering can reflect laser light, and then they can decouple the laser from the target. And also, it is very important to study how much hot electrons are produced. Stimulated Raman scattering and to plasmon decay produce plasma waves, and the plasma waves can accelerate the electrons and produce hot electron tail in the distribution function. So basically, usually in inertial confinement fusion, hot electrons are considered very, very dangerous because they can preheat the target and can make the compression much more difficult. Now, in shock ignition, the situation can be quite different because they are produced by the final laser spike. So they are produced when the fuel is already very thick and dense. And so the hot electrons, if they are not too hot, if they are not too energetic, maybe they will not be able to penetrate deeply into the target. And in this case, they will deposit the energy in the outer layer of the target. And this can be good because they can increase the shock pressure and they can increase the coupling of the laser to the target. Well, this is just a view graph which shows the difference between the classical ablation pressure produced by laser and hot electron driven pressure. In the classical shock generation by laser ablation, the laser energy is deposited at the critical density and you produce a shock wave which travels in the material. And the pressure of the shock wave scales as the critical density to 1/3 and the laser intensity to the 2/3. Now, if you have a very long plasma, actually the laser energy is absorbed even before the critical density. This is called the localized absorption. And then this produces a decrease in the pressure. It produces a decoupling of the laser from the target. Now, in the case of a hot electron beam, this is quite different, because even if the laser is absorbed far from the critical density and the hot electrons are produced far from the critical density, they will penetrate anyway until the dense region, because their penetration is just determined by the total crusted mass. And then they will produce a pressure which scales as the density of the dense material times the intensity to the 2/3. Now, this is not the laser intensity, of course, this is the intensity of the hot electron beams. Of course, you will realize that the hot electrons are produced by the laser beam, so this intensity of the electron beam will be much smaller than the laser intensity. But on the other side, this density, the density of the compressed fuel, is much bigger than the critical density. So even a relatively small number of hot electrons can contribute a lot to increase the pressure of the shock wave. Well, you can show that in order for shock ignition to work, you need to create a shock wave which is at least 300 megabar at ablation front. There is some preliminary experiment which has been done at Omega, which seems to show that we are able today to produce this 300 megabar. But okay, this experiment is a bit delicate because they were not measuring directly the ablation pressure, but they were measuring the time needed by the shock wave to come to the center of a solid plastic sphere. So for sure, they were generating very big pressure. About the number of 300 megabar, maybe we must be a bit more careful. Okay, I just go to the conclusion, and I would like to say that I said before that shock ignition is compatible with present-day laser technology, which means that a laser like NIF and megajoule can make the laser pulse which is needed for shock ignition. They can make this kind of laser pulse with the final spike. But there is a problem. The problem is this, that this machine had been designed for indirect drive. And so the beams, as I said before, do not come uniformly around the interaction chamber, but they come into two poles, high and down. So if you want to make direct drive using this kind of machine, you have to depoint the beams so that all the beams which would come up and down now come all over the surface. But of course, if you have a beam like this which comes on the pole and you depoint it, the focal spot on the target surface will become bigger because the beam will be almost tangential to the surface of the target. So now, if you want a uniform laser intensity on target, you want a uniform laser intensity on target because you want to drive a uniform compression, you must decrease the energy of the beams which have not been moved, the beams which still have a small focal spot, so that the intensity in the small spot is the same as the intensity of the big spot. Well, the result of this exercise is that you start with 1.5 megajoule of laser energy, and if you want to have a uniform illumination, you can only use 500 kilojoule. Well, 500 kilojoule, maybe they will be enough to demonstrate ignition using the shock ignition approach. But before we go to this shock ignition demonstration experiment on LMJ or NIF or on Shenzhen 3, we have to solve a lot of physical issues. like parametric instabilities, role of hot electrons, shock formation, hydron instability, uniformity of compression, and so on. And we have to demonstrate that we can do this polar direct drive. And in order to do this, we can use a variety of lasers, going from kilojoule laser with maybe one beam or a few beams, to lasers like Gecko in Japan, or Shengguan 2 in China, or Omega in United States, which allows for multi-beam irradiation, and finally go to kilojoule, megajoule big laser facility. So in conclusion, I think that shock ignition shows that there is a very interesting physics, which is related to parametric instabilities and hot electron generation. But this physics is interesting, but needs to be understood and mastered. And the physical issue must be addressed in intermediate laser facilities before going to NIF or LMJ. And I believe that this is an exciting field for research in physics for young people at the beginning of their career. So in conclusion, I think that in fusion, we are really entering a new era, because we have facilities like ITER in Cadarache for magnetic confinement fusion, NIF and LMJ, or Shengguan 3 for inertial confinement fusion. And I believe that the demonstration of net energy production will be possible in the few next year. Of course, then we need to define a strategy which brings us from science to technology, to the fusion reactor. And there are still some points which we really didn't understand how we can manage. So thank you very much for your attention. And if you have any question, I'm ready to answer.
Thank you, Professor Batani, for your wonderful talk, because this showed us the technical aspect and what are the physical part that we can include here. Because as plasma physicists in the initial part of their career, something they can address which may have direct application in fusion technology. For instance, regarding the parametric instabilities and other kind of instabilities. Sir, one question
Yes.
for, I think it should be, no one has put, but I think, can you just suggest that is hydrodynamic model, that the fluid model that often we use in plasma analysis, so can it be used, or is it more suitable to use this kind of model in studying fusion plasma, laser plasma fusions?
I'm not sure that I understand your question. You mean if the hydrodynamic?
Yes,
Yeah.
yes. Here I wanted to say that the laser plasma interactions or this fusion technology, which had a lot of parameters to be stressed upon. So as initial researchers in plasma physics who are basically learning the fluid model, and
Yes.
is the fluid model, if they start in their career studying with the fluid model, can some of the details, instabilities and all these kind of things can be properly?
Yes, I understand. But actually, of course, you know that analytical models are very important because they explain us what is the physics which is important in what is going on. So analytical models is something that we should always keep doing and always keeping in trying to improve. Then when you want to do detailed, when you want to make a detailed prediction of what is going on, you have to use simulation codes. And of course, these simulation codes are just the translation of the hydrodynamics equation, but in a much more complex situation. And indeed, this simulation code, let's say, are not perfect, because if they were perfect, we would have been able to demonstrate ignition at the National Ignition Facility. But they say that they are, let's say, quite good. Now, when we go to shock ignition, the situation becomes much more complicated, because the impact of parametric instability is bigger, and you produce hot electrons. And this usually is not taken into account well in the analytical models, and not taken into account well in the numerical codes. For instance, parametric instabilities, hydrodynamical instabilities, hot electron generation, and hot electron propagation and energy deposition usually require a physics which is three-dimensional and require new models. For instance, if you don't have if you don't have hot electrons, you can make a diffusion approximation for your transport of heat into the target. But if you have hot electrons, these hot electrons will have a penetration depth which is much bigger. So you cannot use a diffusion approximation. You have to use a non-local model for heat transport, or you can use a kinetic model. And then everything becomes more complicated, because I mean, we know how to deal with this kinetic model. This you can do with Monte Carlo simulation. But if you want to put this Monte Carlo simulation within an hydrodynamical code, then the calculation time will explode. So we need to develop new models which, in a rather simplified but accurate way, allows to treat in a self-consistent way the impact of parametric instability, the generation of hot electrons, the non-local heat transport, and many other phenomena like cross-beam energy transfer and so on. So there is really a lot of work, and as you said, much work can be done even if you don't have a big laser facility. You can do a study of parametric instabilities, which is interesting, even in your laboratory, for instance. What I think that we need is that we would need some kind of international initiative like ITER for magnetic confinement fusion. We would need something comparable for inertial confinement fusion, which can allow to bring all the effort together, so that maybe you can study parametric instabilities in India, somebody else can study hydrodynamic instability in another country, but then we take care that all these studies are made in conditions which are relevant for what we want to achieve, and we bring all these results together. So this is what we miss in the field of inertial confinement fusion.
Thank you, sir. You had cleared my personal question. So all I think is a collaborative way to deal with the matter, and a proper code to incorporate the fluid models in a physical situation. I think in this regard, the gyrokinetic code is quite a bit advanced. I'm not sure about it, but what are your views?
Sorry?
The gyrokinetic code they are using, some people.
Yes, well, actually, this is another interesting point, because hydrodynamical codes usually neglect magnetic field. And well, we know now the magnetic field, which are self-generated by laser plasma interaction, can be important in the can be important for deciding the growth rate of parametric instabilities, can be important for the transport of hot electrons, can be important for the non-local heat transport. And also, I didn't speak about this at all, but there are new approaches which are trying to make a magnetic assisted inertial confinement fusion. So you put the imploding target in a magnetic field. And in this case, you will need to have codes which are able to do the full hydrodynamics and to deal with the magnetic fields.
Thank you, sir, for this wonderful talk and this recent advancement. So I think the students, they have understood the gravity of the subject and the scope as well, because this field is a new field and has a lot of aspects to venture into. So I hope questions will come later, which I will convey to you, sir. So they will take some time to understand this, because they're master students, and all the details they would definitely go for. And thank you, sir, once again for being with us.
Thanks to you. It was a pleasure to come to give these lessons, and I hope that the next time we will do it in Kolkata.
Yes, sir. We are from Kolkata, just ask you to come again and again, so we'll be able to have a direct interaction with you. And sir, please take care of your health.
And we should also start to implement real scientific collaboration, because it can be useful to everybody.
Yes, sir. We are looking forward.
Thank you very much.
Thank you, sir.
Goodbye.
Bye. Thank you, sir. Well, thank you, students, the audience, and the viewers in YouTube. I found that many are watching live, and this talk was so much resourceful and enchanting, I would say, that many of the young scholars and students will think of getting into this field. So those who are planning to do simulations or analytical models, they can also look into it, but it will require proper understanding. And as sir had pointed out, a good number of collaborative works should come forward. So we hope that we will be moving in that direction. So this webinar and the preceding summer workshop, these two were a step towards in that direction. So let's come back to our students and scholars session once again. So we have now two presentations. One will be a pre-recorded one by Shomu Sarkar. So he is from NIT in Karnataka, and his presentation will start right now, and he is also live. So whatever you have any question, you just put it in this chat box in YouTube. I hope you are enjoying this thing, and let me inform you regarding tomorrow's program as well. After we have two talks, one by Shomu Sarkar and another by Shayan Ghosh. So after these two talks, the session for this evening will be over. And tomorrow we have two invited talks by Dr. Orgho Mukherjee from ISAR Kolkata and Dr. Amar Prasad Mishra from Vishwabharati Shantiniketan. So the title of the talk you can find from our website are Breaking of Nonlinear Waves in Plasma, the Kinetic and the MHD Simulation Approach by Dr. Orgho Mukherjee and Dr. Amar Prasad Mishra from Vishwabharati Mathematics Department. He will deliver a talk on the electromagnetic solitons and their stability in degenerate plasma. So these are tomorrow's program, and the next day we have Professor Naresh Pal Singh Saini and Dr. Subdeep Kaur from Guru Nanak Dev University delivering their invited talks, as well as our student uh, presenters. And on the final day, that is on 11, we'll be having our closure ceremony. But on that day, we will start our program a bit early from 5 p.m. And Dr. Mukesh Ranjan from the Institute for Plasma Research in Gandhinagar, he will be presenting a talk on the industrial applications of plasma. So I think we will cover all the aspects of plasma physics, and this will be a very interesting part. So before we uh, come, I would just like to ask Shomo Sarkar to be live there, and
Yes, sir.
please keep an eye on the chat box if you find any questions. And let's start your presentation.
Shakar from NIT Karnataka. So good evening everyone. This is Shomo Shakar from NIT Karnataka. Chart particle try to go away from that accumulation. And
Well, there was a mistake. I just mistakenly muted the um, video. So I apologize for my inability out here to just for these technicalities. So I'll just get back to the beginning, and thank you for holding your patience. Thank you.
so, good evening, everyone. This is Shomo Shakar from NIT Karnataka. I am currently pursuing my MSc there, and here we have studied the electron acoustic wave and its solitary structure in the presence of Fermi pressure, and you have also studied the the modification of KdV equation into log waves. So we have studied this all in summer workshop on plasma physics, coordinated by Professor Swarniv Chandra. So before starting, I would really like to thank Professor Swarniv Chandra because he has been so much friendly to all of us throughout this whole summer workshop, and especially for me, this branch is very new to me, and he has helped me a lot. So thank you, sir. And I would also like to thank my co-author Tomal Ghosh for performing the simulation part of our study. So moving ahead, in this presentation, we'll first see what is plasma, and we'll then see what is electron acoustic wave. Then one by one, we'll see the dispersion relation, the KdV equation, the log wave, and then we'll see the simulation of KdV solitary structure profile and the log wave, and then we will conclude. So first, what is plasma? As you all know, there are basically five states of matter. First three are solid, liquid, gas. Then comes plasma, and then your Bose-Einstein condensation. So first, if we provide heat to solid, it converts into liquid, and if we heat liquid, then it converts into gas. And if we heat the gas further, almost up to 1000 Kelvin, and so it converts into an ionized gas. But remember, not all ionized gas are called plasma. So to call ionized gas a plasma state of matter, it has to follow some certain conditions. What are those conditions? The first condition is the quasi-neutrality. So what it is? It is that as a whole, the ionized gas should look like neutral. What does it mean? It means that the number density of electron is should be equal to or roughly equal to the number density of positive ions. Because to avoid the your individual effect of the individual effect of particles, right? We'll see it macroscopically. Well, the next condition is the plasma frequency. Well, it often happens that due to the accumulation, due to the lots of charged particle confined in one place, there often happen that you can see some accumulation of charges in places in plasma. So for this accumulation of charges, there we will see some local local electric field. But you will also have to follow the quasi-neutrality. So to compensate that local electric field, the charged particles try to go away from that accumulation. And for these, there also comes the inertia. And for this inertia and accumulation, you will see your oscillation of those particles, and you will have ionized gas have its own frequency. So there are lots of other conditions, but these are the basic conditions that an ionized gas has to follow to be called as plasma. So next, in this video, this is a natural phenomena of what we have studied, the electron acoustic wave. These northern lights, beautiful northern lights. So there is also a shooting star there. It's also made up of plasma. So now we'll see what is electron acoustic wave. So in electron acoustic wave, we basically consider two species of electron. One is cold electron and one is hot electron. There is other species, but we don't consider the motion of ions. We are considered them so immobile because they are much heavier related to the electron. But as you can see, the hot and cold electron, but they are not the temperature is not understood thermally, but it is understood statistically. What does it mean? It means that like if you can see in this figure, there are two Gaussian distribution. One, the right one is for hot electron and the left one is for cold electron. So the T2 is the mean temperature for the distribution of hot electron, and T1 is the mean electron for the distribution of cold electron. So the contradiction is that in this portion of the graph, you can see that there are there can be lots of hot electrons whose temperature are much lower than the temperature of cold electrons, and there are lots of cold electrons too those that are having temperature much greater than some of the hot electrons. So this is the statistical understanding of temperature. Okay. So going ahead, now the boring stuffs. We'll see the basic formulation according to the quantum hydrodynamic model. The first two equation tells you the continuity equation of hot electron and cold electron respectively, and the third and fourth equations tell you the momentum equation of hot and cold electron respectively. So in third equation, in the left hand side, we have considered the inertia to be zero because the motion of hot electron is much higher than cold electron, and in fourth, for cold electron, we have not considered the pressure term because the motion of cold electron is so low that it doesn't impart any pressure on the plasma. And last but not the least, the Poisson equation, which relates the number densities of cold electron and hot electron. So as we know, we are lazy physicists, quoted lab course. So we generally don't deal with unnormalized equations. Rather, we use some smarter technique. We use the normalization schemes and make those equations normalized to make our life easier. So what we do is basically we in normalization schemes we basically replace those unnormalized quantities with the normalized quantities to make it unitless, and then we put it into the equations and get these normalized equations. So for the first two equations there is nothing much changes, but in third and fourth equation you see this H term. This H term is the quantum diffraction term, and in the Poisson equation, you will see the delta. We have taken the delta as the ratio of number density of hot electron to the cold electron in equilibrium. And we have considered the Fermi pressure. So the quantum pressure is basically proportional to the number density to the power some constant. And Fermi pressure is proportional to the number density to the power 3, as you can see here. And also they obviously follow the Pauli's exclusion principle. You all know what it is. So moving ahead, first we'll see the dispersion relation. So the dispersion relation is basically tells you that how the behavior of plasma changes with the changing value of frequency. So what we do first, we first follow some standard perturbation technique. These are the field variables. These are field variables in equilibrium. This is the first part of term, and this is the second part of term. So if you consider that the field variables varies as sinusoidal manner, and we take some partial derivative with respect to space and time, we will get the eigenvalues of those operators like ik and minus I omega respectively, and we replace those operators with its eigenvalues in the equation, and we'll take the first order coefficient of epsilon, and ultimately after some calculation and mathematics we'll get these relation between omega and k. So this is your dispersion relation, and if we plot them, we plotted them with respect to three different parameters. First, first with respect to the delta values, if we take delta value as 1, it means that if you are taking the number density of hot and cold electron almost equal to each other, then you will not see any nonlinear effect. Okay, and if you like increase the number of hot electron or cold electron, you will actually see a effect here and here. Next, for different edge value, you will see for if you increase the edge value, you will get more nonlinear effect. And for streaming motion, first you will see that if you're considering u0 as 0, that means if you are not considering the your relativistic effect, then you will get the least omega value for a particular k. And if you are increasing the value of u0 for a particular k, the value of omega will increase gradually. Next, going ahead to the KdV equation. So first, the KdV equation was introduced by this scientist. I can't pronounce the name properly, so it's something goes in also. Okay, so in 1877, it was introduced by this scientist, and later part in 1895, it was rediscovered by scientist Bordeaux, and he is after whom the KdV equation got its name. So what is basically the KdV equation? It is a third order partial differential equation. It is a mathematical model to study nonlinear waves, and it is the balance between dispersive force and nonlinear forces like gravity, like your electric force and magnetic force. For these balance, you are getting those solitary structure. So here the A is your nonlinear coefficient and B is your dispersive coefficient. So next we will see the calculation of KdV equation in a nutshell. So we basically do the change in variables, and we change the variables S and T to psi and tau, and replace it in the equation. Then we calculate the field variables in terms of potential, and after doing lots of 4 and 5 pages calculation, we'll get this form of KdV equation. So the expression of A and B looks so messy. Now after some calculation more, we'll get the solution of the differential equation. So this here the phi A is the amplitude which depends on the expression of A, and this x is the width of the solitary structure that depends on the expression of B. So what happens is that in different situation, the expression of the expressions of A and B vary, and thus the amplitude and the width of the structure vary, and you will get different type of structure for different situation. Okay, so this is the simulation for our KdV equation. So somehow the time part is got from the screen. So we have taken the initial time as 0 second up to 1 second with the interval of 0.01 second, and we perform the simulation. As you can see, the amplitude is here. The amplitude is almost 1.5, and here the amplitude is much lesser, almost 0.5 to 1. So moving forward, you can understand from this. Moving forward, now we'll see the log waves. So what is log wave? We generally have a misconcept that the tsunami wave and the shock wave and the log waves are basically same, but this is not the fact. They all are basically different from each other, whereas tsunami waves are generated due to the seismic activities. The shock waves are generated due to your eta term, that is the viscosity term, and log waves are generated due to the non-linear effect of waves. So the log waves are much more dangerous than the tsunami waves because it is unpredictable, and this doesn't follow the superposition principle. And in case of astrophysical log wave, the corona mass ejection is dangerous to the satellites and probes. Okay. Now, okay, in this video you'll see two experiments. First one, you will see a spike spike type of log wave for concentric waves. So we'll see a spike here. So a single spike like log wave, and next hold a second. So in this experiment, you will see multiple log waves, spike like this is called the quad spike wave. So these are the, here they are. So now imagine that you are in a boat in the middle of those log waves. So, well, moving forward, we'll see the log wave in a nutshell. So basically the same type of calculation. We'll do a change in variables, putting those in the normalized equation, equating the coefficient of epsilon of first order, second order, so on and so forth, and ultimately we'll get a modified nonlinear Schrodinger equation that looks like this. Okay, so we'll get a solution for the potential, and here the P and Q term. The P term is basically the minus 3 kV, and Q term is basically s squared by 6 pk. Now the condition for log wave is that if the multiplication of PQ is negative, then you will get a log wave that is stable. And if it is positive, then this is unstable. That means you will not get any log wave. So for our test, we got a negative PQ, and we got a structure like this. Here you can see the amplitude is almost 12. So basically we have taken these as not 5 mod square. So if we take the root over of 12, it's almost 3.5. So it is almost twice the amplitude is almost twice the amplitude of normal waves. Now moving ahead, this is the simulation for our log wave. Okay, now we can see the time evolution. So these are the spikes. Look at the amplitude. This is also the 5 mod square. Okay. So this amplitude almost 40. And as time goes, we'll see some spikes also. The amplitudes are much higher, but it is less frequent than the solitary structure, normal waves. So this is the, all of a sudden you will see a spike here. So we have simulated it from 0 second to 1 second. So you will see some sudden spikes here. There is the second one. So it goes like this. So moving ahead, this is a video from NASA where you can see the log waves from coming out from your sun surface. This is the Parker probe launched by NASA in 2018. So by studying those log waves, the scientists are assuming that why the temperature of sun's atmosphere is much higher than the surface of the sun. They are assuming that they are because of those log waves. So here are some two cool pictures, two still pictures from this from the Spider-Man 2, where the villain is extracting his power from this plasma stuff, and here it is the plasma sword used in Star Wars movies. Next, the applications. The most important application of plasma is the power production, as mentioned by one of our previous presenter, the arc reactor that was used in the movies of Iron Man. Is basically a fact. You can actually make a power arc reactor and can make power from those objects. So next, the astrophysical objects. You know that most of the astrophysical objects are made up of plasma. So by studying the plasma, we can have a better understanding of those objects. Now there are laser applications. There are danger from space, as I have already mentioned. The coronal mass ejections. They can harm our satellites. So we have to study the plasma more. And there are lots of other applications like semiconductors and so. So yep. Thank you. This is it. In fact, if you have any questions, you can ask.
Well, thank you. It was a wonderful presentation. And just we come back. Just a moment. I think I'm audible. And there is a question by Tuhin Devnath. Could you please explain again the difference between the shock waves and the ROG waves?
Okay, so
Between shock waves and ROG.
am I audible?
Yes, you are audible.
So shock wave is basically generated due to the your eta term, that is the viscous term, okay, viscosity term. So but the log wave is mainly generated due to the nonlinear effect of waves. Like if you see on the sun surface, that loop type of thing is basically the shock waves, okay. But what I have shown here, that thing is the log wave. So the shock wave is generally created due to the, as I have told, your viscosity term. So log wave is not generated due to the viscosity term, because we have not considered that viscosity term here, but it also but in this case also the log wave is generated. So log wave is generated due to the non-linear term. It doesn't follow the superposition principle. So this is basically the difference between shock wave and.
Your voice is breaking. Shomu, could you just clear on the last part? It is not audible.
Hello.
Hello.
Hello. Yes, sir. I'm audible.
Yes, yes.
Okay, so basically, in our case, we have not considered the viscosity term. So in this case, in our case also, we are getting the log wave. So log wave is basically generated due to the nonlinear effect of waves, right? In an if you are considering the ocean, in ocean it is created in the middle of the ocean. So basically in this the shock wave is generated due to the viscosity term, as you can see in the sun surface, the loop type of thing, that is the coronal mass ejections or also, they are basically the shock waves generated due to the viscosity term. But log waves are not those. They are not log waves. So log wave that I have already shown in our video.
Would you just want me to go to that part once again?
Sorry?
Would you want me to play that video once again?
Yes, sir. Yes, sir.
So good evening, everyone. Different situation.
Is it here where you want? Which part?
Sorry, I can't see those.
Oh,
video.
sorry, just hold on. Yes. Just a moment. Yes. Can you see now?
Yes, sir.
Yes. Can you see?
Yes, but the video is not.
No, I have paused the video.
Yes, sir. Yes, sir. I can see.
Okay. So this slide or any other slide you want to go?
That Parker probe slide where I shown the sun success.
After?
I'm not seeing anything, sir. It's paused.
Eta term, that is a misconcept that the tsunami wave.
After it. Sir, I can't see the video. It's just paused.
Is it paused?
Yes, sir. I can only hear the voice only.
Okay, I think, well, we'll clarify on this later. So as I think he has clarified, that Ishtomo has clarified that shock waves arise due to the viscosity term in the governing equation, and the log waves are generated due to the nonlinearities.
Nonlinear behavior of the waves.
That is generated inside the wave mode. So log wave can happen out of this electroacoustic or ion acoustic, whichever mode you are talking on this. So as CISO in the first day's lecture, CISO Sebastian, Dr. Sebastian has said that very little evidence of shock waves in space plasma is observed, but there is always a possibility that there might be some shock waves, else our equipment, that is satellites and space mission equipments, those things can suffer from various shocks. So right now, thank you. We would like to thank Shomo Sarkar for his presentation and discussions. Now we are with the last speaker of this day, Shayan Ghosh. Shayan, could you just get in with your hello, Shayan, are you there?
Sir, may I present now? May I present now my
Yes,
screen?
yes, you can present.
Okay.
So
Okay.
over to Shayan.
Is it visible, sir? My screen visible?
Yes, it is visible. It is visible. Okay.
Now, myself Shayan Ghosh, and good evening to everyone. And myself Shayan Ghosh, I am doing MSc from Acharya Prof. Chandra College under WBSU. And my title of my today's talk is Effects of Exchange Correlation on ESW in Antirelativistic Degenerate Plasma, solitary waves. Now, and I'm doing this project under guidance of Dr. Swarniv Chandra. He is very much helpful. And this is highlights of my today's talk. What is plasma, or the motivation, and the electroacoustic wave, relativistic degeneracy, quantum hydrodynamic model, linear dispersion characteristic, quadratic KdV-Burgess equation, and solitary structures and resultant references. So my slides are not changing.
Well, you just go to PowerPoint and give your right arrow.
Okay. It's not responding.
I think your
Okay.
cursor, yes, your cursor is with the video.
Okay.
Just open the slide once again. It was moving just, no
It's
issue.
not.
Well,
It's not responding.
Well, would you just like to get away, get out once and come back? That's not any problem.
Okay, sir, my. This is not responding.
Don't panic.
I think my laptop hanged.
Well, we just take a break for 5 minutes until his thing gets off. Just turning off his video. Shan, start again.
Hey,
Start your
sir, off. Oh, yes, it's now.
I opted. I turned it off.
Is it visible?
No, you start sharing.
Okay. Is it visible now?
Yes, visible. Go. You just stick here with the PowerPoint.
Okay,
Yes.
sir. Okay, sir. Now we have to know that what is plasma. In our universe is made up of 69% of dark energy and 27% of dark matter and just 4% of normal matter. And in this just 4%, we all live in, or all physical phenomena are happen, and all physical rules exists. And this plasma is a quasi-neutral gas of charged and neutral particles which exhibits collective behavior. And this is a dilute solution of these charged particles or something. And this is name, or this is one of the 4 fundamental states of matter, and was first described by Irving Langmuir in 1920s. And we know all these 3 states of matter, solid, liquid, gas, from our basic 6 or 7 standard science classes. Now this is 4th state of matter, plasma. By heating solid, we get liquid. By heating liquid, we get gas. And by heating gas with high amount of heat energy, we get plasmas. Now, I have used two terms, quasi-neutrality and collective behavior, in my definition of plasma. Now, quasi-neutrality is that plasma is a mixture of positively and negatively charged particles, ion and electrons, in which negatively charged electrons are almost completely neutralized by the positive charge ion. And this neutralization factor is enough that we can take the value of uh, or the density of electron and density of ion as equal, and this density is called the plasma density, and is not so neutral that all the existing electric field lines will be vanishes. And this is the collective behavior. Collective behavior means the motion depend not only the local conditions but on the state of plasma in remote region as well. And we know that plasma consists of charged particles, and they behave collectively due to the attraction or repulsion causes, and this interaction process caused due to the electric field produced by the free charge particles. Again, the slide paused.
Use your keyboard, right arrow.
Yes, sir, right arrow, I am using this, but slides are not moving.
You close your PowerPoint, go back and come. Well, it is always possible to face some problems.
So can I do this presentation in this mode?
The same thing. You go to F5.
Okay.
Present.
Now, the criteria for plasma.
Or else you can.
Plasma.
Yes. Go.
Yes, sir, it works. Now, plasma in an ionized gas, but not all ionized gas is plasma. There are three conditions that have to satisfy to be plasma. First criteria for an ionized gas to be plasma, that is, it has to be dense enough that the Debye length, lambda d, has to be much smaller than the length of plasma, L. And the second condition is that the number of particles in the Debye sphere has to be very large, that is satisfied the collective behavior. And the third condition has to do with the collisions. And if the omega is the frequency of typical plasma oscillations and tau is the mean time between collisions, then with the neutral atoms, then we required the multiplication of omega and tau greater than 1 for the gas behave like plasma. And this is the summarized conditions for behaving ionized gas like plasmas. And now we are dealing with quantum plasma. There is classical plasma as well. And a plasma becomes quantum when the quantum nature of particles significantly affects its macroscopic properties. Now the properties of quantum plasma, it has to be very dense, and its temperature could be low because we worked with cold electron as well, and overlapping thermal de Broglie wavelength and quantum degeneracy term. We have worked with two hot and cold electrons. And where it occurs in white dwarfs, neutron star, galactic plasmas, intense laser solid interaction, biophotonics. And in this graph, we show that for temperature less than 5000 Kelvin, we get solid particles or classical plasmas, but for temperature greater than 6000 Kelvin or more, we get quantum plasma, and every white dwarfs or neutron star exists here. And this is the image of white dwarfs. Now, white dwarfs is such thing that it is very dense, heavily dense, that its radius may be comparable with the 100 times smaller than our sun, but its mass is equal to our sun. So even a teaspoon of white dwarf matter is as heavy as an elephant on this earth. And this is a neutron star kind of things. And the motivation behind our work is to investigate the solitary structure of electron-acoustic waves in degenerate quantum plasma, including relativistic effects. The present work is to investigate the linear and nonlinear properties of electron-acoustic waves in relativistically degenerate and dense quantum plasma consisting to distinct group of electrons. and stationary ions, and study the effect of quantum diffraction parameter, viscous force, exchange correlation on the condition of formation and solitary structure properties is our basic motto. Now we have we are dealing with this electron acoustic wave. There are many waves as well, like ion acoustic wave or electrostatic wave or dust ion wave, acoustic wave. Now electroacoustic wave is that it occurs in the plasma containing two distinct species of electrons like hot and cold, and the frequency is high enough to comparable with the ion plasma frequency, and the phase velocity is much higher than the cold electron and much lower than the hot electron. Now, the plasma with two distinct group of electrons mainly occurs in space plasma and laboratory experimental plasma as well. This scientists Yang and Zhang worked with the space plasma in 2007, and Diffler and Simonen, they worked with laboratory plasmas in 1969. And we have used to explain, we have used electron acoustic waves to explain the source of broadband acoustic noise and wave emission in different regions of Earth's atmosphere. For this all studies, electron acoustic waves become one of the most important areas of research in plasma physics. In this image, we can see that this is solar wind, and there can be shock waves or anything, CMEs, anything. This interact with the Earth magnetic field. And after interacting, there is the energy accumulation, and there is the energy consumption. And this radiation belt is called the Van Allen radiation belt. And for this interaction, we can see this aurora kind of beautiful visuals. This is aurora kind of things, and as well as the geomagnetic storms on the Earth magnetic field. Now, the relativistic degeneracy. We have taken the relativistic pressure, relativistic effect. So we have to know why we have to study the relativistic degeneracy. The works have done in most of the cases in electron acoustic waves in classical and non-relativistic plasma. But most of the astrophysical objects are like white dwarfs, neutron star, etc. are highly dense in nature. And in this case, we have to study the degenerate and relativistic plasmas. Now we are coming to the reason why we have to study the relativistic cases. When the density is very high, the average interferometric distance becomes equal or less than the thermal de Broglie wavelength. And for this, the quantum degeneracy comes. And at extreme high degeneracy, the thermal pressure of electrons may be negligible compared to the Fermi degeneracy pressure, and which comes due to the Pauli exclusion principle. And in such extreme condition, the electron Fermi energy, this is the expression, may be comparable to the rest mass energy of electron. This is mc square, and the electron speed approaches to the speed of light in the vacuum. This is the relativistic case. In such cases, we have to study the relativistic and degenerate plasmas. Now we have dealing with a quantum hydrodynamic model. Now, quantum effects in plasmas are usually studied with the help of two well-known formulations like Wagner-Poisson and Schrödinger-Poisson. Wagner-Poisson dealing with the quantum kinetic behavior, and Schrödinger equation hydrodynamic behavior in quantum scales. Now, quantum hydrodynamic model is derived by taking velocity space moments of Wagner equations. Now, quantum hydrodynamic model is widely used to describe the dynamics of plasma particles in quantum scale. And due to this model, in this model as an extension of classical fluid model in plasmas, this model is an extension of classical fluid model in plasmas, where the quantum correction term bomb potential comes into action in the momentum equations of the charged particles. The extra term gives rise to new aspects of collective interaction at nanoscales. Now, these all are the dynamic equations that we have worked with. We have worked with the three component plasmas, like hot electron, cold electron, and the stationary ions. The ions are stationary, so they will not have any continuity equation. This first one is the continuity equation for hot electrons, and this second one is the continuity equation for the cold electron. Now, this third equation and fourth equation are the momentum equation for hot electron and cold electron. In this third equation, we can see that this first term is the electric field term, and the second term is the pressure term, and this third term is the quantum diffraction term, and this fourth term is the exchange correlation term. And in the fourth equation, we can see the effective derivative term, and these all are explained. And this fourth, in this last term, in the fourth equation, this is a viscous coefficient, and viscous force term this is, and this is the dissipative term in this equation. And now this fifth equation is the Poisson's equation, and we have to deal with Poisson's equation because we know that plasma consists of charged particles. So this Nc is the density of cold electron, and this Nh is the density of hot electrons, and this Ni is the density of ions. Now this Uxc is the is the exchange correlation term. Now we have worked with pressure law. We have worked with electron degeneracy pressure that was introduced by Chandrasekhar in 1939. Now, after implementing some degenerate and relativistic configuration, we can express this in this following form, this pressure term. Now, in this pressure term, this Rj is the relativity parameter, and it varies with this electron or something density, electron density, hot or cold, maybe that. And this Rj is a constant, this ratio of equilibrium densities. And now, after implementing some condition like relativistic parameter for weak relativistic, like Rj tends to 0, and for ultra relativistic term, for Rj tends to infinity, we get this two pressure term expression. And we have deal with this ultra relativistic case, that is Rj tends to infinity. And this equation, pressure varies with the density, with the 4/3 power of this density. Now, this is the normalization schemes. These are all are the normalization schemes. We have to normalize all the terms, make dimensionless. To make dimensionless, we all normalize these terms. And this is the Fermi velocity term. And after normalizing these basic equations, we get this normalized equations. Now, this first two is the normalized continuity equation for hot electron and cold electron. And this eighth equation is the momentum equation for the hot electron, normalized momentum equation. In this H comes due to, after normalization, that quantum diffraction term, this is bomb potential. And these lambda terms, these two lambda terms comes due to the, after normalization, the exchange correlation term. And in this, the same thing. Now this delta is the ratio of cold and hot equilibrium electron densities, and this is the expression for lambda 1 or lambda 2 and this bomb potential term. Now this linear dispersion characteristics, we have used the standard reductive perturbation technique, and this perturbation expansion of the field quantities like densities of this hot and cold electron, velocities of hot and cold electrons, and this potential term. And using this perturbation expansion and using the standard reductive perturbation technique, we get into this linear dispersion relation. This is our linear dispersion relation. And you can see that I have taken this positive root of this equation due to this is the first process. And in this case, the frequency will be larger than this from this negative root. Okay, and this is the frequency, and k is the wave number. Now this all A, B, C are the constant, and these all are the values of this constants, and these all are the constants in this value of C. Now the linear dispersion characteristics. After plotting the linear dispersion, we get this linear dispersion characteristics. This is for different values of H, that means bomb potential. This is for different values of delta, and this is for different values of streaming. That's like U0. And you can see that with the increasing value of H or delta or U0, the frequency is increasing. The frequency all time is increasing linearly. And in this, the extreme position, that the extreme value of frequency and wave number, in all cases, in this time, in this term, and in this, we get some damping effect. And this is due to this viscous force and exchange correlation. There with the energy loss. Now we come into the KdV-Burgers equation. Now, following the standard reductive perturbation technique, we use the usual stretching of space-time variables, that is x and t. This xi and eta, and xi and tau, and eta in this term. Now solving the lowest order equation with the boundary condition like psi tends to 0, xi tends to infinity, we are going to the next higher order terms of epsilon, the perturbation term. The following usual method, we obtain the desired KdVB equation, and this is our KdVB equation, this 15th equation. In this equation, you can see that this n term is the nonlinear coefficient, and this d is the dispersion coefficient, and this r is the viscous coefficient. Okay, and these are the expression for this coefficient, nonlinear coefficient, dispersion coefficient, and r, and all constants they are here given here. Okay. Now the solution of KdV-Burgers equation. To find the solution of this equation, we transform the two independent variables like xi and tau in terms of psi. And after implementing some boundary condition like psi tends to 0 and phi tends to 0 and del phi del psi tends to 0, we come into this solution of this KdV equation. This phi is equal to this term, and this is a tan hyperbolic solution, and this first term is the 1 minus tan hyperbolic square, that means sec hyperbolic square. Okay, then here the d and n and r, I have already explained this nonlinear dispersive and viscous coefficients. Now the solitary wave profile. You can see that this is for low viscous plasma. This graph I plotted for low viscous plasma, eta less than 1 or equal 1 values. Now for different values of H, that bomb potential term, we get in the negative psi region, and we can see that in the negative psi region and positive psi region, there is a potential difference. You can see that. And this is come due to the viscous term and viscous force. And we can see that increasing value of H, the amplitude and the width of the solitons are increasing. And this is not anything else. This is the 3D version of this graph. Now we're coming to this graphs. This is for low viscosity plasma as well, and this is for high viscosity plasma, and this is for the for varying eta, the viscous coefficient. Now we can see that for low viscous plasma, when we take eta less than 1, we get potential difference. There's Burgers like curve, but the potential difference is not very large. But when you can see this for high viscous plasma, when we take eta greater than 1, 3, 6, 9, the potential difference is huge. You can see. So we can say that this Burger-like expression, or this this energy loss or this potential differences come due to this mainly due to this viscous force or this viscous coefficient. Now in the negative psi region, for increasing eta values, the potential are decreasing, and in the positive psi region, with increasing eta values, the potential are increasing. In this case also the same thing happened. Now in these curves, we have plotted for high viscous plasma and high viscous plasma for changing U0. Now you can see there is a discontinuity for value of 0.7. Now why get that? We get that basically due to we have a term called like V0 minus U0, capital V0 minus U0, the phase velocity and the streaming, and you can see that we take V0 is equal to 0.7 and U0 is equal to 0.7, so that terms goes to 0, and for this situation we get this discontinuity in this curve. And in this curve, we can see that we take the value of U0 from 0.6 to 0.2. Now, for values of U0 greater than 1.1, we get some compressive type solitary structure, and for less than 1.1, we get some rarefied solitary structures. And see that. Now, in the solitary profile for high viscous plasma, for different values of delta, we get here we can see that for value of delta less than 0.4, we get this compressive type solitary profile, and for delta greater than 0.4, we get this rarefied type solitary profiles. That means this for this the potential is positive, and this for this the potential is negative. And this is basically the 3D plot of this curve, not any different kind of things. Now, this all are the summarized results that I have already discussed with you all. Now, further studies, the double layer type of solution I want to do on KdV-Burgess equation and the multi-stability analysis. Now, this is the ITR India. This is a huge project, and this ITR, that means International Thermonuclear Experimental Reactor, this full form. This is the, am I audible, sir?
Yes, you are audible. ITER is a project in which ITER India is a part that is looking
Okay,
into.
ITER India is a part of this project actually. Now, ITER India is a part of this, and the motto of ITER is a very large thing. We all know about nuclear fission and fusion reactions, but all the reactors throughout the world are basically nuclear fission, not nuclear fusion. And the motto of this ITER to and the energy of sun, we know that the energy of sun is basically due to the fusion reaction. So we have to know the criteria or the source or something details about this fusion reaction. So the motto of this ITER is to build our own sun on our earth, and to study this earth and know about this fusion reactor. And our India's contribution in this ITER, the biggest contribution this ITER from today's is the largest refrigerator or freeze. We can easily understand that in nuclear fusion or any nuclear reaction, there will be produce some high amount of heat energy. So for cooling this, that instrument will be used. So, and India became a full seventh partner in ITER in December 2005, and it is located in Gandhinagar, Western India. Is the Indian domestic agency to design, build, and deliver Indian kind of contribution to ITER. Now, this is a chocolatey universe version in the vision of Devi Prasad Duwari sir. This is like a desert kind of thing to you all from myself. And this is all are the references. These all are the references I've taken. And the acknowledgement, I want to acknowledge and express my immense gratitude to Professor Dr. Swarniv Chandra to give me this opportunity to work in this project and guide me throughout this work. And he's very helpful, very much helpful. And I express my gratitude to my group partners, Protoy Saha, for his immense support. And I am grateful to my friend Tuhin Devnath as well for his PC advice. I'm grateful to my parents also for the love and support. And this is the contact details. This is mail ID of mine. You can contact me through this. Thank you. I've ended here. If anyone has any queries, then they can ask.
You, Shan,
I'll try
for
to.
your wonderful presentation.
Welcome.
So we have some applause and some queries. So the first question comes from your friend. Hopefully you have thanked him. He's Tuhin Devnath. So his first question, he has got two questions. The first question is, can you clarify when we get compressive and reactive solitons? And number two is, what is exchange correlation? The first one,
okay,
when we get compressive and reactive.
Okay, the compressive and rareficative structure we get basically due to the, you can see, I'll go to the slides. Now in this case, for the compressive solitary structure, you can see this is positive potential. And when we work with the positive charged particles, that like ions, we get the positive potential. And in this case, usually we get this type of compressive solitary structures. And when we work with the negative kind of potential things, like negative charged particles, like electrons, then the potential will be negative as well. So we will get the negative potential structures like rareficative structures. And in this case where I get this, you can see that in my Poisson's equation, there is a delta term. I think in the lower value of delta, this is you can go to this equation. Now, when the delta is very low, then the negative this density term blows up. So then will be the density of NH can be larger. So the positive characteristic maybe comes out for these cases. I think I clarify this question. What is the second question, sir?
The second question is, what is exchange correlation?
Okay, exchange correlation. Wait. This term is called exchange correlation, and exchange correlation is a new thing in research of plasma, and very new thing. And exchange correlation is the exchange of energy when the charged particle is moving, and this expression can be derived, can be expressed in this form that the exchange correlation potential with the ratio of exchange correlation potential with the density. This can be used, and the effect of exchange correlation, I am showing that in my dispersion curve. This damping caused due to the energy loss for exchange correlation and viscous force, basically.
Well, thank you, Shayan.
Clear?
It was a great presentation, and you have got a lot of admirers who are, among them are
Thank you.
Onusri, Shomo, Protoy, Arnav, and Isha Prabhahini De. So these people
you.
and the rest have appreciated your talk, and it was really an informative one. So just stop your presentation. Well,
Okay, sir.
thank you. So thus we end the
Thank you,
sixth day. Yeah. Thus we end the sixth day of our webinar, and tomorrow we have two guest speakers and two oral presentations by students. One will be by a group of 3, and another will be from Egypt, Demeter University, Nora. So she will be presenting. So hope for the beautiful presentations tomorrow and the 2 days after till 11. So I thank you for being a part this evening, and thank you for your patience, your interest, and all your love that you have given to these young scholars and the organizers. And we are very lucky that we are having celebrated personalities who are presenting their talks. So let's thank today Professor Dimitri Batani for his mesmerizing talks for 2 days. And tomorrow also we have Orgo and young scientist, Orgo Mukherjee from INSAT, and one of our senior, Dr. A.P. Mishra from Vishwabharati Shantiniketan. So we have their talks tomorrow, and the day after tomorrow we have 2 more invited talks, and finally the last day we'll have some eventful. We are planning for it. So thank you. Thanks to all of you, my viewers, my participants, my presenters, and all those out there who will be watching later. So have a good night. Thank you. Namaskar.